My clicker working. There we go. So we're off. To start out, I'm going to ask a question. What is this? Anyone? Can you shout out? We've got fire. Yeah, we've got fire. It's not a system outage. It's fire, warmth, light. It could even be Prometheus. However, we're going to refer to it as a signal here today, and we can put it on top of a watchtower to signal something's happened, maybe an oncoming attack. We can then use these watchtowers to help defend our town. I work for a games company, so I like to use pixel art and games when we're describing stuff. As an attacker approaches, we can light the signal fire to tell our town that an oncoming attack is coming. However, as we grow and our city spreads out, we need more towers to signal that an attack's coming. So we build out more towers. Now when an attack comes, the first light goes up to signal that an attack's coming. It then propagates back to tell the town that the attack is coming. However, in this point, we tend to lose some resolution. The three signals at the bottom have now just become one. Here we see a goblin that mans the middle tower. This is David. However, he's quite forgetful. He only ever remembers the past 3 days of when attacks have happened. This isn't great. Also, we sometimes have sneaky enemies whereby they come in stealth and take out a tower, and we don't actually know an attack's coming at that point. Now, this can be thought of as signals being passed around by watchtowers back to our town, or it could also be thought of as Prometheus recording metrics back up to something like Grafana. Now, all these problems in the tower defense are a lot like we could have with this Prometheus setup. I'm Dominic Green. I am a software engineer at Improbable. I work on a number of open source projects such as Thanos, Go gRPC middleware, and Go HTTPwares, and also organize a number of meetups in London.
My name is Lucas Serven Marin. I'm a software engineer at Red Hat by way of CoreOS. I'm working on the observability team on all things Thanos, Prometheus, and Prometheus Operator. And without further ado, today we're introducing Thanos. This is an open source project dedicated to providing a global query view of metrics, providing a scalable and highly available metric system, and also long-term retention with unlimited storage. So, a little bit about the Thanos community. This project was started 2 years ago by Fabian Reinhardt and Bartek Plodka at Improbable. And since then, it's grown into a CNCF Sandbox project with 8 core maintainers and hundreds of contributors. And yeah, hopefully some of you will also become contributors in the future. Since then, it's also been adopted by a bunch of different companies, so don't just take Dom's word for it or my word for it. We're running it, but so are a lot of other people. And today we're actually going to start our discussion not with Thanos, but with Prometheus. We're going to specifically look at some key features of how Prometheus works. We're going to look at some of the shortcomings of Prometheus, and then we're going to look at how we can use Thanos to complement these shortcomings in Prometheus and fix some of the scalability issues that we might run into.
Okay, to start, we kind of want to have a shared understanding. Now, this is a quote from the Google SRE book. It signifies that monitoring is the art of collecting, aggregating, and displaying real-time quantitative data about a system. So Prometheus, and by extension Thanos, are monitoring systems. We've built Thanos on top of the shoulders of giants, so we've used all the components of Prometheus to build out a metric system in a distributed way. If you can put your hands up if you've heard of Prometheus before, fantastic. And keep your hands raised if you're using it in production. Amazing. And anyone using Thanos in production? Oh, cool. Nice. A lot more than I expected. So with Prometheus, on your client side, you instrument a number of metrics. You expose these via the Prometheus server, which is an HTTP endpoint, which then Prometheus can grab these metrics from. On the right-hand side, you can see a number of servers. And on the left, this is Prometheus split down into 4 key components: the scrape engine, the query engine, the compactor, and the rules engine. And we're going to take these components and distribute them with Thanos.
Cool. All right, so to begin, let's just take a look at a really basic Prometheus deployment in Kubernetes, where we have a number of microservices being scraped by one Prometheus server. And let's think about what happens, for example, if for any number of reasons our Prometheus goes down. What happens to our entire metric system? And let's think about, more specifically, what were to happen if Prometheus went down right in the middle of an incident. We're having a production outage, and right when we need metrics most, Prometheus is down. At the heart of it, the issue is that Prometheus itself is not a highly available system. So the way that we deal with this in production oftentimes is we run Prometheus pairs, right? So we'll run two Promethei, one next to each other, where both are scraping all of the services. Obviously, one of the results of this, we're running two Promethei. We're also using twice the resources, CPU, memory, disk. But keep this in mind, because we're going to come back to this setup a few more times. Another limitation of Prometheus today is a storage limitation. So by default, Prometheus has, as we all know, a retention of 15 days, right? So if I ingest some metrics, these samples are kept in TSDB for 15 days. And the question remains, what if I want to query data from several months ago or a year ago? And moreover, what happens if something happens to my disk? What if my file system gets corrupted for any number of reasons and I lose all my metrics? Now what do I do? At the end of the day, we want to have some way of providing long-term storage for our metrics and some way to make sure that we don't lose our metrics when we need them the most.
So not only that, is when we start to scale up Prometheus, we tend to do it by a Prometheus federation. So we have a monitoring cluster that federates out to a number of other things. And at this point, you need to set up recording rules at the start. You can't get the fine granular details that you can do from your Prometheus in your leaf clusters. And so at times, your engineers end up going from the main cluster at the top out into the leaf clusters to try and get more detailed information. And then as we scale up, maybe we want the federation to have HA as well. At this point, we're now scraping double the amount of data from the clusters at the bottom. So we're actually, and then when they go HA as well, you're doing 2 for 8 times the amount of data. It's a lot of bandwidth we're wasting by just scraping metrics. Normally, you have federation so that you can propagate queries and use it with your Grafana setup. This is relatively okay. With 3 clusters, you can pull the data into memory. It works fine. Federation, what effectively does is pulls all the data from those leaf Prometheus into memory to then be served again. However, when we scale up, if we have then n number of clusters, that's all that memory is coming into that federated endpoint and going to blow up that instance if we're not careful.
Right. So this is where Thanos comes in. The whole point of Thanos is to try to combat some of the issues that we see when we're stretching Prometheus to this really global scale, when we're scraping from hundreds, thousands of different clusters. The question is, how can we make Prometheus scalable and highly available? So at its core, Thanos consists of a number of composable components that we can use to bring scalability, HA, long-term retention on top of any existing Prometheus setup. With that in mind, the goals of Thanos is, number 1, to be Prometheus compatible. This is not just something that's convenience. This is actually strategic. We want Thanos to be built on top of all the great design principles of Prometheus, to leverage all of the knowledge and all the learnings from the last several years of running Prometheus, and to leverage the Prometheus ecosystem. Number 2, we want to have a global view of metrics at query time. We want to be able to see metrics from all of our different clusters. We want to have long-term retention. So we want to be able to see historical data from several years ago from all of our clusters. But also, we want to be able to see data down to the individual sample, even if it's from like 2 years ago. And that brings us to the 4th point, which is we want to provide downsampling and compaction of this data so we can make our queries efficient. So let's do a thought experiment, and let's think back to the federated Prometheus setup that we were just discussing earlier. At the heart of it, one of the issues with this setup is the fact that we're ingesting data from n different clusters into one single instance, and this can bring scalability issues. But let's just think for a minute, what could we do if we invented a new component where instead of ingesting data from every single cluster at the leaf, we actually query data at runtime? So, for example, this querying service receives a request from a client, it proxies it down to the leaf clusters, joins the responses, and returns that to the client. Let's imagine something like this. Suddenly, our service for querying becomes somewhat more scalable, right? We're not ingesting data from every single cluster, so we are just dealing with queries, and this becomes somewhat tenable. There's one limitation here. One big problem with this design is that every single time that we get a request, we have to proxy it to every single cluster. Imagine that we are querying for data for a time series that's only on cluster 1. We're nevertheless going to proxy that query to every single other cluster, and that's really inefficient, right? So let's imagine for a minute if we could instead add yet another component, and what this did was a sidecar that was sitting next to Prometheus and just announced, hey, these are the metrics on my TSDB on this local cluster. Now, Thanos, or this new component that we're imagining, this query component, can know ahead of time, hey, if I get a request for this metric, I know which cluster I have to hit. And we're no longer having to make requests for every single other cluster, and we can make our queries more efficient. We can optimize this a little bit more. If you recall, here we're exposing two API endpoints, one for the Prometheus query MPI, and one for this new imaginary announcing metrics API. If we combine these into one single API that does both querying and announcing labels, we can also take advantage of this moment and say, hey, rather than exposing the query data, the results, using JSON, what if we did it using protobuf? And this way, we reduce the load at the query side on the query component because we no longer have to do all these extra allocations, CPU, blah, blah, blah. And we can also reduce our bandwidth usage. So let's expose one gRPC API that does both querying and announcing to make this more efficient.
So at this point, we've effectively designed the Thanos query component and the Thanos sidecar. The query component fans out and calls to each sidecar, which then does a remote read to the local Prometheus, exposing the information about the data that's stored on that node. Now, this communication is all done via gRPC, and one of the most important parts of Thanos, in my opinion, is the store API. So this API is what's exposed, is a subset of the RPCs that's exposed by all the things within Thanos. So here you can see the info endpoint, which gives us the metadata about the time and the kind of data that's on that node, as well as the series, which gives back a streamed response, allowing us to query or send that data more efficiently. To get more information about the store API, Bartek and Frederick are going to be doing a deep dive tomorrow, so head over to that to really dig into the store API. So as it turns out, we've also solved the HA problem, at least for the federated instance. Here now we have Grafana calling in, and it can round robin between two query components in that monitoring cluster. This means that if one goes down, the other one can still serve traffic, and it's just proxying requests through. We can also use the same thing to do HA Promethei in the leaf clusters. Here we can see that the store API now knows about many of the Prometheuses. However, we've just got the same problem as we had with federation earlier. We now have to get back all the data from both of those sidecars and the Prometheus, and we're then combining it in memory in the query and sending it back to Grafana. I wonder if we had a component that could combine multiple streams of data and feed it back. Well, we do. That's the query component. So what we can effectively do now is put the query component down in those leaf clusters along with the sidecars. This means that when we call into the querier, we can then merge the two streams and send it back. As I said before, the store API is really important in Thanos, and this, the query component, along with the sidecar, implement that API, so we can just switch them in when we need to. So here we've made a lot of progress towards a scalable Prometheus system, but what about storage? We said we also wanted to keep the data for longer.
Right. So we already know of one really obvious solution for storage, and that's object storage. This has the benefit of being both really cheap and, on the other hand, super flexible and scalable, right? Most cloud providers don't require you to pre-allocate some amount of storage for your object storage. So we can actually upload blocks as we need, and the storage will just grow with us. So one solution that we can do is say, hey, let's make our Thanos sidecar upload TSDB blocks. As Prometheus produces these TSDB blocks, these immutable blocks, we can have the sidecar upload them to object storage, and now we suddenly have a way to keep long-term data. So let's make sure that, if the storage on the clusters died, we don't lose any of the blocks. However, one of the things that's missing here is we need a way to expose the long-term stored data to the rest to the query API. So one thing that we could do is imagine yet a new component that is a gateway to this data stored in object storage. We already have an API that we defined for querying and announcing the metrics that are stored in some storage, and that's the store API. So let's make this component, the gateway, expose the same API, and when it receives a request for querying some metrics, it simply reads those metrics from object storage and returns it to the querier. Now, we've solved the question of how do we store long-term storage, how do we store long-term metrics, and also how do we query for long-term metrics. But one of the issues that comes with this great new power is the following. Imagine that we query for 2 years worth of data of some time series that's sampled at 15-second interval. This will be hundreds of thousands of data points. And this presents a number of problems. Number one, we're doing a ton of disk reads, we're using a ton of bandwidth, and then we're returning more data points than we probably have pixels on our dashboard. So we're doing all this work for no reason. One thing that would be great is, hey, if we query for a ton of time, for a really long time range, let's only use maybe one sample every hour. So what we want to do is downsampling of our data. For this reason, let's invent yet another component called the compactor, that what it does is downsamples all of the data that's stored in object storage, and it also compacts multiple smaller TSDB blocks into a fewer, larger ones so that we can make querying more efficient. Also, if you're interested in more in knowing about downsampling and how that works, again, please see Bartek and Frederick's talk tomorrow at 5:20, and they're going to be talking about this.
Cool. So we've seen how we started out with a federated Prometheus. We've gone from there to add the query component to allow us to proxy traffic out to multiple sidecars. The sidecar then is taking those requests and proxying it to a Prometheus with the remote read and uploading blocks into object storage. At this point, we've added in the store gateway, which can read data from that object storage and serve it back using the same store API. And finally, we've had the compactor, which can downsample and compress data. Now, this works great for us at Improbable, whereby we've got tens of clusters, maybe up to 40. We can add these store APIs into our query components, for example. But as you get to bigger scale, this might not work for you, especially if you're creating and destroying clusters on the fly.
Right. So one of the things that we're doing at Red Hat is that we have thousands of OpenShift clusters that are sending thousands of time series back to a monitoring cluster that we're running. And one of the issues that the traditional Thanos setup presents is that we can't ask all of our customers that, hey, open up your Prometheus endpoint for us so that we can query it. Number one, that's unsafe. And number two, even for us, that would be really cumbersome because we have to manage configuration for every single customer cluster as it goes up and down. So this model just simply won't work for us. What we need to do is switch from a model where we're pulling metrics from all of our customers' clusters to one where the customers' clusters are pushing metrics up to us. Luckily, such a model already exists in the Prometheus ecosystem, and this is called the Prometheus Remote Write API. So let's do one more thought experiment. And let's say we want to invent one new component that is able to accept remote write requests. And what it does is that when it receives a remote write request, it stores these metrics in some local TSDB that it's running in memory there. Now, one thing obviously that we're going to need to do to make this component useful is that we need to expose the same store API that we implemented in the sidecar and the querier and the store gateway. And this way we can query the metrics that are stored in the local API, or in the local TSDB. So far so good. We now no longer require our customers to open up a port, right? They just remote write the metrics directly to us, and we no longer have to manage configuration about information about all the customers' query endpoints. So far we've made a lot of progress. But as we start scaling this up from a few clusters to n clusters, we're going to run into an issue. This is looking a lot like the same Prometheus Federation setup that we had at the beginning, where we have n clusters, thousands of clusters that are all writing data into one single process that's ingesting it. This, at one point, is going to hit a limit, and it's going to break for the same reasons. So we need to do something to make the system scalable. One way that we can solve this is by turning our new component into a hash ring. So let's say we make this component a scalable hash ring that we can grow up and down to suit our needs, as load grows. And these components will take care of forwarding requests to each other, and we can load balance all incoming requests among them. One detail that we have to make sure when we're creating this hash ring is that we want to make sure that all samples from one given time series always end up in the same replica, so that way the time series is coherent in one single TSDB. And this will solve the scalability question, because now we can grow this hash ring as we need. But notably, this doesn't yet solve our high availability issue. So imagine that one of the replicas in this hash ring goes down. This means that all time series that are destined for that replica will no longer be able to be accepted. So clearly, we need to do something. One way that we can address this issue is by implementing replication. And we can say, for example, hey, all incoming time series have to be replicated to 3 different replicas, and unless they're accepted by 2 replicas, we don't mark the request as successful. Now we can suddenly tolerate replica failures, and we can adjust the replication settings. Obviously, we can say replicate to 5, it must meet at least 3, blah, blah, blah. And this way, we have both scalability and high availability. So we've addressed 2 of the concerns. We still have a question about storage. How can we make the data that's stored on the metrics that are stored in these new components that are receiving metrics, how can we make this also long-term and durable? Luckily, we've already addressed storage before with the Thanos sidecar. And what we can do is say, hey, let's make this same component upload all the data to object storage.
So yeah, here at this moment, we can then have that component upload its blocks, much like the sidecar does, and then add back in the store component that we had earlier. So this store gateway will proxy traffic, and the query can not only query the hash ring, but it can query out to object storage. This sounds like it would work. So now we can use that to get the historical data as well. And this effectively is the Prometheus remote receiver. So this allows us to use the remote write to store data and upload it to object storage. If you want to know more about the remote receiver component, Matthias is giving a talk tomorrow, and he's going to show how you can use it in the wild. So go along to that talk and heckle him. So the last thing that we haven't talked about, though, in the 4 quadrants we saw earlier, was the fact that we could send alerts and do recording rules. At certain points, you may want to record over multiple clusters of time series. For instance, the maximum number of players in a game server across multiple clusters. This is where we can use something a lot like Prometheus recording rules. So we've taken those and put them into the Thanos rule. However, alerting rules, we should make sure we push right down the stack, more close to where we actually take the data. So at this point, again, we started out with Prometheus in almost like a federated way. We've now added the query endpoint, which will query data anywhere. We've added the remote receiver that we can do remote writes to. Again, we've got the object storage satisfied, and then we've added a rule component to allow us to add multiple metrics from clusters together or send alerts to Alert Manager.
All right, so let's take one last look at our functional diagram for Prometheus and see how this diagram changes now that we're adding in Thanos to the mix. So the first thing we did was we decoupled querying from scraping. We saw also that by running a stateless query component, we're able to provide a highly available querying service. Next, we saw that by exposing metadata about what time series are stored where, we're able to make this querying more efficient. And we also saw that we can provide an additional way to ingest metrics, namely with remote write. We also saw that we can persist these metrics in object storage to provide long-term storage for all of our data. We saw how we can query the data that's stored in object storage using the store gateway, and also how we can make this query more efficient using a compactor. And finally, we briefly mentioned how we can use the Thanos ruler to provide recording rules for the data that's being received from all of the different store APIs. And by doing all of this, we just built Thanos.
If you want to give Thanos a try yourself, And we've actually uploaded the scenario to Katacoda, so you don't actually have to download it and install it and run it. You can go to this website and use it online. However, it is relatively easy to download and run yourself. And with that, thank you very much. So these are the other talks that we mentioned. Deep dive tomorrow afternoon, and that's it with the remote receive component tomorrow as well.
And we're happy to take any questions. One second. Can you repeat the question, please?
Remote receive, is it being used at any scale in production at the moment?
Yeah, we're using it right now inside of Red Hat. And we're using it to, like we said, ingest data from thousands of OpenShift clusters. And this is going to keep growing. We're going to start doing tens of thousands of time series from different clusters.
We've got a couple more over this side.
I'm making the runner run. So you've got long-term storage now where you can store for years or something, but let's say your storage isn't infinite. How do you then expire storage or expire metrics from your storage?
So at the moment, correct me if I'm wrong, I don't think there's anything that automatically expires storage for you. However, because it's in blob storage, it's literally just folders and files in object storage, so you can very quickly purge the old ones if you wanted via a command. I think it is something that the team are looking into for the future, but it's definitely not there at the moment.
Right. It's also really easy to clean up blocks that are stored in object storage, because the way that the Prometheus TSDB format works is that all blocks are named with a ULID that's a universally lexicographically sortable ID, and the first few bits of it are a date, so you can just sort even in AWS or anywhere you want and say, hey, anything that's before this name, essentially this lexicographic sorting, just delete it or something.
Hey, could you talk a little bit more about the configuration of two Prometheuses which are still running within the customer's cluster, within Kubernetes cluster, and how do you configure remote writes, what do you do with batches, and for how long do you store the data locally there?
Right, so when Prometheus is remote writing to Thanos, this is actually just tailing the write-ahead log. So it's not like remote writing the data that is already written to blocks on TSDB. It's actually remote writing what it has in the write-ahead log. What else? Any remote write requests that fail will get buffered in memory, and Prometheus will keep trying to retry those remote write requests.
So take it from the client side, it's just the URL to upload.
Exactly.
Instead of remote write.
So it's just the URL. Oh yeah, sorry, that was the question. Yeah, so just the URL that you configure. You can also adjust some other things if you want, like relabeling configs, and obviously some proxy and other settings and things like this. Yeah.
I went to the Cortex talk. Can you give a brief difference between Cortex and why would I run Cortex versus Thanos?
So both of them are quite similar, and the communities actually work very closely together. So actually, I think the guys are going to cover it tomorrow, but there's a number of components within Cortex that we will also be helping contribute to and use. So they kind of complement each other. Cortex started off with the push-based approach, whereas Thanos started off with the pull-based approach. And I suppose it comes down to, at the start, it came down to which approach you wanted to go with. I suppose the solution is a bit more difficult now that we both have the pull and push model.
Yeah.
Any other question?
Hi, how does this work, or does it at all, with, say, Glacier class storage for?
I don't actually think we have anything that writes to glacial storage at the minute. However, I suppose you could set something up in your object storage to take it out.
You set the lifecycle rules to the bucket, and the bucket will, over
right.
time, move it to
querying, I'm not
Glacier.
sure. So I suppose you could put in cold storage your data if you don't want to read it. So if you don't want to query it, because I'm not sure we could get the query to do that.
Yeah. It'll probably be too expensive to be querying stuff that's in Glacier, because the whole point is that you're not accessing it frequently, right? So you wouldn't want to put things there that you're actually going to be accessing often.
But what about for forensic investigation for something that might have happened,
So, I mean,
months ago?
yeah, if
Would it work?
I mean, you could definitely set up a cron job to copy the blocks across into glacial storage from the bucket, yes. And to do that investigation, you'd then have to just take it back out of glacial storage.
Okay, thank you.
I think that's our time. We're going to stick around for a while, so if you want to ask any more questions, come and grab us or any of the other members of the team.
Thank you very much.
Thank you.